So we got this partial flashing of a mixture, and we have a liquid containing 50-50 or equimolar composition of N-heptane and N-octane. So technically this is normal. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay. Something like that. As you can see, those are miscible. There will be non-polar mixture, and they will form homogeneous mixture. They are at 30 Celsius, and it's going to be vaporized at 1 atmosphere. The main idea is to vaporize 60% of the feed. So let's pay attention to this. This does not mean that this is literally F. They want to vaporize that. So if we were to assume a molar basis of 100, then we will have a 60% or 60 mole amount in the distillate, and in the liquid we will have 40. And of course we are not paying attention that much into the compositions right now. Right now we only know that XF equals 0.5. We want to calculate the vapor's final composition, which will be this one right here. Okay guys, so the solution will be the similar approach. We will select a basis for calculation, 100 mole. You can choose 1 mole if you want to. I prefer 100 mole. And I am using another notation. Remember that C is also used for the inlet of the feed. You can use XF or CF. Those are the same. And E is 0.5, and because this is equimolar. And as stated before, the bottoms will be 40, the distillate will be 60. Now, right now, you don't know the compositions, you don't know F, so it's kind of hard to get this equation right here. We just know 0.5 here, but we don't know F. But one quick way to verify for F, the slope right here, the slope will be equal the bottoms divided by the distillates. So try to rationalize that, and this is essentially because the vapor will go here to the distillates, and a 1 minus the vapors will be, by definition, the bottoms. So hopefully you get the idea of how do we get this slope. Essentially what we are doing here is simply the ratio between these two species. We get minus 2/3 or minus 0.667. And now it's time to identify in the plot the following. So first things first, we gotta find our point in the 45-degree line in which x equals y. Remember, this gotta be 0.5, 0.5. Then we draw the operation line given the point and the slope, and then find the t value in which we are going to have the equilibrium conditions. So in the diagram, first things first, let us identify the xf value. Technically we have cf for now, which will be this p point. Okay, so now we have this point. Second point will be to use a slope of minus 6.6667, which is 2/3. Remember, it's changing y in changing x. So let's go literal, okay, or that would be something 1, 2. So we change 2 and we go 3 on the top, will be 1, 2, 3, will be something around. Okay, there's no space. So it will be, let's go for the other approach in which we, for every unit we go, we increase 2/3, which will be something around that. So let's try to build a line through this point. As you can see here, guys, we have the point of intersection with the equilibrium line. And if we go to the left side, this will be something around 0.58. And if we go down, will be something around 38. And those are the compositions of the most volatile component, that will be N-heptane, which is C7. And in the liquid, let's say this will be in the vapor phase and this will be in the liquid phase. In the vapor phase we have 0.58. Technically speaking, if you were to use numbers, you will get 0.575. And in the liquid phase, we will get 0.38. And that's our final composition. So guys, why can we do this? Because we know the slope and we know this point value and we have the equilibrium line. So if we wouldn't have the equilibrium line, we wouldn't be able to do so. But we do have the equilibrium line and we do have the operation slope or the operation line. So this is a very quick example on how easy it is to use the graphical method for flash distillation.